FAA presents Jim Bede, designer and builder of new types of airplanes for general aviation. His sensational bullet-shaped Bede-5 has become one of the most publicized sport airplanes ever introduced. Here on videotape, he discusses topics common to all aircraft design.
We're going to be discussing aerodynamics for ground vehicles. This can be automobiles, trucks, race cars, what have you. The aerodynamics on a ground vehicle has, just in the past 5 or 7, 8 years, become a real knowledgeable, known factor to be considered. Prior to this, automobile designers, truck designers were aware of the basic problems involved with aerodynamics, but somehow it was always put to the side as not being very important to deal with. With the energy crisis, the idea of trying to make our vehicles more efficient immediately brought in the aerodynamics of ground vehicles as the forefront of being important. The realities of it is, it should have been important all along, because there is a variety of reasons why we want to be concerned about the aerodynamics of a ground vehicle. If we try to ask the question why be important about it, there are several factors. One, very obviously, is drag reduction. And the reason we want to reduce the drag is because we can increase the speed and we can get more efficiency out of it. A second reason is handling, the actual load on the tires, as well as several other factors that get into it. The stability in crosswinds. When you're driving along on the highways and you encounter crosswinds, the actual stability and the handling of the vehicle is important. And then there's another thing, just plain smoothness and noise reduction. These are 3 basic fundamental reasons why we should have to worry about the drag of a ground vehicle. Anything we can do to reduce the drag will definitely be of a benefit. There's no disadvantage in reducing the drag of the vehicle. And in most cases, it actually makes the thing more attractive, it improves the aesthetics of it, and therefore I think everyone, no matter what kind of vehicle they're concerned with, should do what they can do, what is practical for the basic vehicle they have, to reduce the drag of it. Let's see just how really important this is. A lot of times I've heard the question, or the statement being made, that since an automobile drives along at only 30 miles an hour, 50 or 60 miles an hour, the drag is not important. Well, that isn't really true. It is always important. Drag, due to aerodynamic effect, is just like driving around with your brakes on. Is it not important whether you have your brakes dragging at 30 miles an hour or 60 miles an hour or 70? Should you only be worried about having your brakes on when you're doing 100 or more? Of course not. We do all sorts of work in trying to put real good bearings in our wheels and try to have beautifully designed drive shafts with good bearings to reduce the friction of that. We go through a tremendous amount of bother of designing our engines to get the absolute maximum efficiency. We come up with very sophisticated combustion chambers and spark plugs to get 1 or 2% improvement of horsepower. We do all of that. We do an excellent job of it. But yet, when it comes to what is that horsepower being used for, it's being used to move the vehicle down the road. We just want to completely ignore the aerodynamics of it. You know, any vehicle, automobile, truck, whatever it is, once it gets moving, once it gets up to speed, there are only 2 fundamental things that require horsepower. One is the rolling resistance, the wheels, the tires against the ground. There will be resistance there. It takes power, takes torque of the engine to overcome that. But there's also the aerodynamic drag. If we could take a vehicle on the moon, for example, and put it on steel rails where there is no air, there'd be no aerodynamic drag, the rolling resistance would be nearly 0, you could get to 60 miles an hour and with practically no power, or maybe none whatsoever, the thing would just coast forever and ever. As long as you could eliminate the drag of the rolling resistance, and of course you have no aerodynamic drag because there is no air. But here on Earth, we do have aerodynamic drag all the time. And it's not easy to reduce it. I mean, we're starting off with something that has a tremendous amount of drag, or normally a boxy looking vehicle going down the road. Why not get it down to a lower level? We don't have to make it zero. We can't make it zero. We don't have to reduce it down to extremely low values. But if we do cut it in half, that will make a significant improvement in the performance of our vehicle, and it's easy to cut in half. Just take a look at this for example. If we have a streamlined shape that is 4 foot in chord, and it could be any length we want, and we have a round rod 3/4 of an inch in diameter only, just a small 3/4 inch rod, the drag of these two items at any speed is exactly the same, whether it's 30 miles an hour, 50 miles an hour, 100 miles an hour. Now, how many times have you seen a round 3/4 inch bar sticking up on a race car or on an automobile or on a truck or something like that? That could be replaced by a streamlined airfoil section that is 4 feet long. Obviously, if you take that 3/4 inch diameter and make it streamlined, you would cut the drag down tremendously. This is actual drag. This is pounds of force. This is just like dragging the brakes or using very, very poor bearings on it. Here's a relatively simple formula you can use in actually determining the amount of drag. This is good for sea level conditions, and it is based upon the drag of the vehicle is equal to the drag coefficient times the density ratio times the area, and the area depends upon what kind of drag coefficient we're dealing with. Most of the time in automobiles, the drag coefficient is based upon the frontal area. So normally this term here is the frontal area of the vehicle. This is the speed in miles per hour divided by 391. Basically, here's what it's saying. Drag again in pounds, the actual number of pounds of resistance you get. If you use the area in square feet, the frontal area in square feet, use the speed in miles per hour, and this is the density ratio. It's 1 at sea level, so since you're really not concerned about it at altitudes, you can always use this term as just 1 or simply ignore it if you want. And the drag coefficient, this is a dimensionless figure that is based upon the relative resistance of something. If the drag coefficient is 1, then that is basically what a flat plate going through the air, straight right angles to it, would have a drag coefficient of 1. If it's streamlined partially and has a drag coefficient of 0.5, then it means it is half the drag of this flat plate. If it's 0.2, then it's 20% of that flat plate, and so on. So it's always a relative figure. Don't be confused by the fancy term of drag coefficient, but it is a relative relationship of comparing that value to another value, and by using it within the formulas, you can then come up with a precise drag force. Let's go through a real quick example here. Let's take a Volkswagen Rabbit, for example. The frontal area is about 22 square feet. The drag coefficient is around 0.46, which is not real good, but it's a lot lower than it would be for a convertible, you might say. It's a lot lower than a man on a motorcycle or something like that. The drag coefficient here of 0.6 is very typical of most vehicles. If we look at it at 60 miles an hour, density ratio 1, we then come up with the drag, using all the numbers in there, of 93.18 pounds of drag at 60 miles an hour. If we really want to know how much horsepower that has taken, the actual horsepower to overcome nothing but the drag, we can use this formula. Horsepower is equal to the drag times the speed divided by 375. Here it is, drag in pounds, speed in miles per hour. It's 14.91 horsepower. So Volkswagen Rabbit, having a drag coefficient of 0.6 at 60 miles an hour, needs almost 15 horsepower for no other reason at all except the aerodynamic drag of that. Well, 60 miles an hour is a modest speed, but it's not really all that fast either. Let's take a look at what this would be at higher speeds. Obviously, if you go slower, the drag goes down and the horsepower goes down. But even if it drops, even you're going to 30 miles an hour, why not reduce it down to a much lower level? But look what happens when you go to higher speeds. 60 miles an hour took 93 pounds or 15 horsepower. At 100 miles an hour, takes 258 pounds and 69 horsepower. At 120, takes 372 pounds of drag and 119 horsepower. At 180, which is pretty fast to get a VW going, but if you were going 180 miles an hour, you have 838 pounds of drag and 402 horsepower would be required to take a 22 square foot frontal area having a drag coefficient of 4.6, I'm sorry. If you would reduce it in half, if you take that drag coefficient to 0.20, which is a little bit more than half, of course, at 180 miles an hour, the drag would only be 364 pounds, and the horsepower would be 175 horsepower, as compared to the 402. So there's a significant reduction in horsepower required, particularly, of course, when you're talking about anything that has speed to go with it. Let's just see how this affects trucks, automobiles, and race cars. In the case of trucks, you've all seen the aerodynamic shapes that they put above the cab portion on it. Well, in a truck case, we're really not worried about speed of the vehicle. We're not trying to make it go from 55 miles an hour, which is the legal speed on the road, to 80 miles an hour, 100 miles an hour. But we really are worried about efficiency. We're worried about drag reduction. The most amazing thing is that there are so many different devices that are on top of trucks right now, and obviously all of them must work, but really some work a lot better than others. Let's take a look at a typical one where we would see the basic cab and of course the trailer portion over here. One type is where they use a relatively smooth, streamlined, curved surface over there. That is probably one of the better types that are available. There are types, I think, that are used on a variety of trucks that are, of course, curved not only from a side view, but from a top view. And this, of course, is equally as important because when you're driving down the road on any kind of vehicles, only on a dead calm day is the wind coming straight down with no angle of attack, if we want to call it that way. Anytime there's a wind blowing, and if the wind's blowing any direction except the direction you're driving, you will have a crosswind effect. So from a top view, you have your vehicle like this and the windshield. It's good to have some degree of curvature into it because if the wind is coming off in this direction in here, you want to have somewhat of a proper flow to go around there. Now there are some devices, and you'll find, of course, many, many shapes, but once in a while you'll see something going around where it has sort of an inverted wing sticking on top. This system must work to some extent, but it really has to be a relatively inefficient device for reducing the drag of it. Somehow people get the impression that if you take this wind and blow it up and over the trailer here, that's going to reduce the drag. Well, frankly, yes, it does. It reduces the drag on the trailer a little bit by trying to throw the wind away from it. But what you reduce here, you've picked up by taking this airfoil, this inverted airfoil, and try to spread the air around it and throw it. That isn't what is going to do much good. It probably was better than just the blunt body you had going through the air as it is, but not very good. What you got to do is take a look at some of the real fundamentals that are going on here. Let's take any shape we want to do. Let's take a streamlined curved shape. And I'll make that a little bit more symmetrical. There's a couple things we just have to understand here that's going on. When this thing is going through the air, let's assume this is a cylinder, or we can consider it like a wing, a long section in here that has this streamlined cross section. In any event, assume it's a cylinder now, a streamlined teardrop going through the air. The whole thing we're looking for is to be able to go through the air or have the wind blow over, whichever way you want to look at it, and we want to disturb the least amount of molecules we can. So when it's all over with and passes here, we want the wake, the turbulent air, to be as small as possible. That's the fundamental objective we have. But since it is of a certain width, and the air starts to come along and starts to flow over this thing, we are going to, without a doubt, have to move the air around to make room for this solid object that's starting to come through. Well, several fundamental things happen. Number one, as the air starts to flow around it, if this is nice and smooth, it will stay attached, it will stick to it, and it will flow very, very nicely. It is slowing down in one sense, and then it has to speed up over here, and as it speeds up, it actually reduces the pressure and sucks this thing forward slightly. Now as it continues to flow over the streamlined object, now it starts to slow down again and eventually comes back into here. And as it's doing that, it pulls back in this direction here. This is a little bit lower pressure. It tends to suck this body backwards. The total summation is, of course, the final force will be a resistance or a drag pulling you backwards. But if it wasn't for this smooth, streamlined shape up front here, this drag would be considerably greater. So what you have done is gradually spread the air out, made it smooth, and as it went around this forward portion, it actually did suck the vehicle forward slightly. If it's a very streamlined airfoil section like on a wing, it will do a great deal of suction forward. Then, of course, you have the resistance of the surface and the pressure back in here, which tends to pull it back. But this becomes nominal if this is working. If, on the other hand, this is just blunt and squared off, then, of course, the air will come, hit it, and go around it very sharply, separate, become all turbulence on it. You will not only have the negative pressure back here, but you will have this tremendous turbulent air that will suck this whole vehicle backwards and nothing up front, literally trying to pull it forward. So the forward section is important to deal with because if you streamline it, make it smooth, let the air stay attached to it, you're going to get some pulling forward. This is based upon, of course, a pressure up front here pulling forward, pressure in the back here pulling back. You, of course, always will have the skin friction of the air right up against the skin giving it resistance. You can't help that. You can make it smooth, you can wax it, but in practical measures, there's only so much you can do with it. You have to expect that. Of course, that'll give you your final wake and your final drag. But assuming you've got a reasonably smooth surface around in here, then, of course, you'll have your drag about as low as you can get. Now, if you start to stick things up, let's say you put a little block right in here, well, that's a pretty bad place to put that little block because this is where the air is actually speeding up. For example, if this thing's going 60 miles an hour down the highway, the air going around this actually speeds up. And when it's passing this region here, depending on how thick it is, it might be going 80 miles an hour. So if you put a little block sticking out there, a little disturbance on the thing, again, it's having the same amount of drag as if it was going 80 miles an hour down the highway instead of 60. And this turbulence in here not only increases the drag of that, but it affects the drag of this portion in here. So where it's the widest of any vehicle, you'd like to do the best you can to not add any additional prototurbulence or any additional drag on it. So fundamentally, on an object like this, we have three basic areas of concern. First is the frontal zone in here. If this can be smooth and streamlined, we can have a definite drag reduction because this portion will actually try to suck the vehicle forward. The widest region in here, what we now have is relatively high velocity and skin friction. We'd like to reduce the skin friction as much as possible by not having any more things sticking out here where we have the higher velocity. And then on the back side over here, we have a pressure that is sucking the vehicle backwards plus the skin friction. If by chance we don't have something streamlined like this and it's actually blunt over here, we now get definite flow separation in here, and we got a tremendous amount of turbulence in here. This area would be considered base drag. This is the drag of this whole object, and the width of it over here constitutes the amount of base drag you have. So you got the frontal region, the midsection, and the rear section, which is the base drag. And this is pretty common on most vehicles, of course. Let's take a look at what a top view of a truck might be, a typical truck would be. This would be the top view. The shape of this region in here controls how much drag reduction we're going to get from the forward portion. Anything we can do to make this smooth. If we can't make the entire vehicle totally streamlined, fine. But anytime we can get any portion of it, anything we can do to make this smoother, we're going to get a significant reduction in drag in this forward portion. Anything we can do to the sides to keep them relatively smooth. And many truck trailers are relatively smooth, considering reasonable manufacturing techniques and so on. Back in here, we will have a tremendous amount of base drag. Unfortunately, because of highway regulations and everything else in lanes and the economics of getting the greatest amount of volume in the truck, there is not much we can do about the base drag in here. However, there are some things that could be studied. We could maybe put little surfaces along the sides in here, something like that. Anything we could do to reduce this wake back in here to get it narrow will have a definite effect on reducing the drag of it. Again, what we want to do with the truck in here is not necessarily try and get higher speeds out of it, but we sure as heck would like to reduce the amount of drag so that we require less horsepower for any given speed, and that will burn less fuel and we get far more efficient. One time in driving a Winnebago motorhome, which is, top view is very boxy looking like this. You can drive here with your window open and put your hand out in the stream like this, and you'll be doing 60 miles an hour, and instead of feeling the wind blow in this direction, try it sometime, you'll see the wind blows forward. Now why is it doing that? Well, it's doing that because as the air came along here, some went over, but a great deal had to go around. It had to go around and go out so far out here like this that you actually cannot reach it. You can be driving that vehicle and stick your arm out as far as you can go, and you'll probably have to go 3 feet out there before you'll finally feel the stream of air that is now flowing around that vehicle. Well, the amazing thing is, here is this motorhome going through the air, which is almost 8 feet wide. It is producing a wake around it that is so big that actually this vehicle could have been designed to be that wide, maybe twice as wide, if not at least 12 feet wide, and it would have the same amount of frontal drag that the Winnebago has, being only 8 feet wide. In fact, once you have this condition, once you have the wind blowing forward in here like this, now you might as well put some mirrors in there. In fact, you might as well mount a little parachute back here and let the parachute flow out and help suck you forward. I mean, if you're going to be that dirty and that much turbulence in here, gain some of this wind that's going forward. Where's this wind going? It just goes forward until it gets to the slipstream and sucks in and pulls back in here. And it's, of course, the end result is you're getting this tremendous wake down the highway, which is doing nothing but slowing that vehicle down a great deal and requiring actual gallons of fuel to push it through the air. It would be a relatively simple thing to make this smooth and streamlined. Forgetting about the sides, forgetting about the back, forgetting about the bottom of the vehicle. Just this portion in here. What is going to happen here? Now the air is going to flow and stick very closely to the side of the vehicle and have a significant reduction. Probably 30–40% reduction in drag if this portion here could be round and streamlined and smooth. When we start talking about ground vehicles like this and we start talking about the drag reduction, it's just like saying that we're going to start off wanting to make our engine better. And what we've got is a little 2-cylinder, 2-cycle engine that has a compression ratio of maybe a 4:1 with a real poorly designed spark plug and a real lousy carburetor. And somebody says, take all the technology you know about automobile engines and designs and improve it. Well, you know doggone well that you don't have to be much of a genius to make that engine one heck of a lot better than it was before. You're starting off with something that's really very, very poor. We have the technology of aerodynamics now to make this thing significantly better. Not 2 or 3%, but many, many times better. Now, when we start talking about automobiles, in that case, we may not only want to reduce the drag to get better fuel economy, but we may want to reduce the drag to get better speeds out of it. We definitely would like to reduce the drag to make the vehicle drive smoother and actually have less noise. Now, this is something that's rarely talked about, but when you take any automobile up to 80–90 miles an hour, you feel a shaking in the vibration condition. I used to always think that that was the tires just riding against the road, and because of the speed, you automatically had that vibration. Not until we designed the Lightstar vehicle, which is a very streamlined little motorcycle, that has a real low drag coefficient. That drag coefficient is 0.092 without cooling drag. And if you consider cooling drag on it, it takes it to 0.094. But in any event, it is very smooth. At 80, 90, 100 miles an hour, that vehicle is extremely smooth going down the road. You can just feel like you can take your hands off the wheel, put it behind your head, and almost go to sleep. It is very, very comfortable, very, very smooth. No vibration, no shaking, no nothing. And besides that, the wind noise is really very, very low. You can hear the tires, you can hear the engine a little, but you actually do not have that turbulent air. And what's wrong with making your vehicle quieter? What's wrong with making your vehicle smoother? It comes to you free. All you have to do is get rid of all that resistance that you had built into there. But when you start talking about an automobile, we have to take a look at some fundamental things. One thing, from an aerodynamic standpoint, this is a pretty good sized box. This windshield here if it could be sloped better, would reduce the drag, but only if the front end is reasonably streamlined. If you have a very blunt front end like you had of automobiles of just 4 or 5 years ago, the airflow coming around here would become so turbulent and separate off of here, become so turbulent that you can have the windshield almost straight up and down, and it won't change the drag much. Why? Because the front end has already screwed up everything. But if you have a reasonably decent front end, which is what some of the newer automobiles are starting to get into, you're starting to get into a reasonably decent shape, you will now start to get reasonable flow across the hood of it. Now once you do that, now you have to be careful of how you're handling this windshield. Not only is the slope of it in this direction important, but of course the side view, the curvature as it flows around. Some of this air as it starts to go will go over it, but the air that's in either side near the fenders and so on, it won't go over, it'll tend to go around it. If you can make that smooth and streamlined, you will have reasonably attached flow. So you can take care of this front region reasonably well, and some of our newer automobiles are starting to get that way. This, of course, is going to give us very big blunt area and base drag that's going to be high. There's no question the air is going to separate as it comes off this region here. There's no question the air is going to separate here. Another region we have is the belly of the vehicle, the bottom of it. Just because you can't see that doesn't mean that you don't have drag there. Of course you have drag. In fact, the drag is even worse than if it was on the side. And the reason for that is you have ground effect. Now, how do you take into account ground effects? Well, it's really somewhat complicated to be concerned about. But one of the ways is to visualize that you have this vehicle going through the air and you have another one, a ghost of it, completely upside down over here. Now, just imagine you could take two automobiles, stick them together, wheels to wheels, and push them down through the air. Well, what you can see here is that the drag of this wheel and the drag of this bottom here will actually start to flow up and do this to it. Well, that's the same thing that is happening here. The reflection of off the ground is one way to sort of look at it. This bottom portion, all the prototurbulence sticking out there, will actually be reflected by the ground itself, and that turbulent air will come back up and strike those things and have additional drag in here. If this was out in the stream and there was no ground in here, there would be somewhat less drag on the bottom as compared to when it's actually up against the ground. So ground effect does take in account here. It adds to the drag of it. It's real important to make this smooth. It's real important, and it's not very difficult to do. Why not do it? Just because you physically can't see it, just because it doesn't add to the aesthetics, is no reason why you can't apply that for aerodynamic reasons, and it will do a significant effect on it. What we can do back in here to streamline this thing, well, of course, you can look at the possibility to streamline it like this, but you can actually streamline it from a side view, too. You could actually have something that would look maybe like this, but from a top view came down and was that degree of streamlining. Now we'll get into this a little bit later, what this has to do with crosswinds and side forces on the vehicle. It's a little bit complicated to how you handle this, but this region here, that's easy to start to make that smooth and streamlined. It's easy to make the sides nice and smooth and clean without any more prototurbulence sticking out than necessary. The back region, that's a little bit trickier, but again, there are things that could be done there. We want to do this to our automobiles for all those reasons. We can get better speed out of it. We can get better efficiency out of it. We'll get less wear on the engine for any given speed we're going at. We'll get a smoother ride out of it. We'll get a terrific noise reduction out of it. But when we start talking about race cars, now we're really talking about something that really adds up and really is important. In the case of a race car, we really want speed. Speed is the most important thing we'd like to have for any given amount of horsepower, obviously. That's the purpose of the vehicle. And of course, if it's also racing around a track, it has to be concerned about its handling characteristics. Now, the design of the suspension system, the design of the tires, all of those things will add tremendously to how the vehicle handles. But you can assist the handling of it by increasing the download, by allowing the tires to have greater traction to the ground itself. And you can do that by using the aerodynamics of the vehicle. You can actually produce a greater download on the vehicle. The problem is whenever you're producing this download, you're going to do this with some form of a wing, and that's the best way of putting it, some streamlined airfoil-shaped device that's going to pull down. When you pull down with it, you're going to have the drag of that wing, and you're going to have the induced drag of it. In other words, not only is the shape of this wing going to produce drag, but the fact that you're pushing downward, that you're lifting downward, shall we call it, that has an additional drag force to go with it. So good aerodynamic principles are used in designing an airplane can now be applied here. If you have some airfoil section on your race car that is pulling the vehicle down, why not use good aerodynamic principles in designing an airplane wing? Use it in a way that makes it the most efficient to do. If we want to take a look at a basic race car, we want to do two things here. I mean, this is the objective we'd like to do. We'd like to reduce the total drag of that vehicle, if we could, to as low as we can. And we'd like to produce as much download as we could, and we'd like to do it in the right proportions. There, of course, is the ground effects type of vehicle where we get a skirt relatively low to the ground in here, and we do certain things with it to try to reduce the pressure underneath the vehicle itself. Well, this is a ground effects process, and aerodynamically it's sound and it has some good values to it, and it, of course, will produce a downward load on the vehicle. How it's shaped and what its proportions are will have a big effect on what the actual download that the aerodynamics apply on the various wheels. If the shape of the thing is peculiar, you may get too much of a loading on the rear or too much loading on the front. If you get real clever about it, and I haven't yet seen one of the race cars done this way, but maybe they are, if you get real clever on it, you can actually maybe control the amount of loading from one side to the other, but that requires a little additional fancy work to be done in there. But fundamentally, what we're trying to do here is have a skirt section in here such that we have a close clearance between the road and the vehicle itself, and we want this to essentially become some form of a chamber, and we want to reduce the pressure in here. And the way we want to reduce the pressure is by sucking the air out of it and doing it. Now, this is going to cause drag. Just sucking that air is going to cause additional drag, but it may be worth it because of the download that it can produce on it. Of course, other methods of doing it is putting wings in the front and wings in the back in here. Obviously, you need to have a proper balance. You don't want to put some aerodynamic wings in the back in here and produce a terrific download, which, of course, will put a download on the rear wheels, but actually will tend to pivot it and reduce the load on the front wheel. So you've got to have a proper balance. You've got to do something up forward here to try and pull the forward portion down in equal proportion, or whatever proportion you decide from your suspension system, from the handling of the vehicle, as what you want to do. Without going into a lot of details, because we can only go so far into this design, we will study each one individually. Let's take a look at the front wing section in here, because actually it's a little bit easier than the other portion. Let's just assume that this is the nose, and let's assume now that we have a wing section that looks like this, and here's the ground level, and here might be our wheel. First thing is, this airfoil section now is operating in basically smooth, streamlined air that's coming toward this vehicle. Obviously, if it's in the wake of another race car, something like that, it has that turbulence. But let's assume for our study purposes here that this is relatively smooth air coming into it, and this wing can now operate with pretty well assumption that the air is flowing straight towards it, parallel to what the ground is doing it here. What we would like to do, of course, is produce the maximum amount of download we could for a given size of this thing. There's no use having this any bigger than we need it, because the bigger it is, the more drag it's going to cause. The more efficient we can throw it down, this load down, and not produce a drag load, the better off we're going to be. Unfortunately, I see a very large number of wing sections that are done up in here, which aerodynamically are not the best. You'd never find these on a real airplane flying along. Let's start talking about that just a little bit here so you get some better understanding what that would happen to be. Let's draw it as a normal aircraft wing would be. This would be a typical airfoil section. And as it approaches the air at some given angle of attack, it's going to produce lift in this direction, and it's going to produce drag in that direction in here. Now, this is what is called a standard airfoil section without any kind of flap on it. If we want to put a flap, a surface back in here like this, we can do that, and that will almost double the amount of lift that this surface will produce. For a given amount of area, you can just about double it, and in some cases even greater than that. Of course, it will also increase the drag. It will more than double the drag. But it will be pretty effective. Now, there are various types of flaps you can use. You can use split flaps, plain flaps, slotted flaps, and so on. But rarely will you ever find a wing that is shaped like this, that has a gradual curvature to it. That, if it's a solid object, is considered a highly cambered airfoil section. Now, there were studies and wind tunnel tests made of these things back in the early 1930s, and they're not used on airplanes for one reason. Why? Is because the amount of drag they produce for every pound of lift, or in the case of an automobile, downward force, the drag is much higher. These are more efficient. For any given amount of area, you can make this more efficient. If you have a fixed number of pounds you want to pull down, by going to this system, you can have less square feet, therefore less drag. So fundamentally, we don't want to use a highly cambered airfoil in the inverted section like this. That's not really very practical. What we really would prefer to do is to have this stopped and have a flapped section in here like this. That will be far more efficient, far better all the way around. The second thing is, when you take a look at what this midsection is, it's looking like it's almost operating at zero angle of attack. Well, on a flapped wing, on a normal flapped wing, with the flap down, this airflow here should be somewhere between 12 degrees to maybe even 18 degrees of this region right here, this line right there. And then this thing should be deflected maybe 30, 40, even 50 degrees compared to that line. So it should be a great deflection. I think a lot of work should be studied in trying to develop a good airplane wing design with flaps and putting it on this forward section in here. In fact, maybe it should be looked at as not even having a flapped section. Maybe you can just go into a nice streamlined airfoil at a given angle of attack. This would be inverted, something like this. Given angle of attack, streamline, and you will end up with all the download you need for the given amount of area that you're allowed to have to produce the adequate amount of download. But at least this flow in here is now operating in somewhat of free stream. Another thing you have to really consider, though, is if this surface is right in front of the wheel itself, being relatively large in diameter and width, it's affecting the flow even before the flow gets to the wheel. If this airfoil wasn't there, if that airfoil section wasn't there, the air coming along in here, some is going to want to go around and some will want to start to go up over this wheel already. So that has to be taken into account. Now maybe some of you people who would like to improve your race cars don't have access to big expensive wind tunnels. Well, that doesn't mean that you can't learn something about this. You can actually take your vehicle out. You can build a grid out here with little tufts of yarn, pieces of yarn or string sticking out, and see how the air is flowing. Take the wing off, for example, and drive the thing only 60, 70, 80 miles an hour, and take photographs and take video movies of this region and see how the air is actually flowing around there. There's a variety of ways you can do things to get visual inspection of what the airflow is doing and see what's happening. Now, if you see how the airflow is coming right in this nose section here without the wing on, you'll get a better idea as to what you should do with the wing, but at the same time, remember, once you put the wing in there, you're now going to affect it again. So after you've done it, then do another grid and take a look at it. You can put a grid out front here, and a grid would be nothing more than taking a frame and putting some wires, and you can do it every 3 inches or whatever you want, and put tiny little pieces of yarn, mount it out on front there, and watch what's happening to the airflow. Put a grid back in here if you want to and see what's happening there. Or you can put actual pieces of toughened yarn all over the wing section itself and all over the nose section and see. You don't need a wind tunnel. You can do this out in the free air. It doesn't give you all the information you want to know, but it tells you an awful lot of what would be helpful in improving the thing. Let's go back here to the rear section. One thing every once in a while I happen to see that as an aerodynamicist you have to shudder at, and as sometimes you will see a race vehicle or something like that blend off, and a wing will be installed right in here, right over the body, and it'll be attached into it like that. Well, this is doing some good, but it's really doing, it's fighting itself. Because what's really happening here is that just like on this wing, let's take this wing right down in here. As the air is flowing over here, it's reducing the pressure considerably over the top of this wing and raising the pressure in this part of the wing. Now, if you take that and turn it over, you've got the negative pressure here, which is what you want, the positive pressure, which you want here, so you think you get a nice download. Well, maybe if you actually put strain gauges on that wing, you'll find out it's pulling down pretty good. But what is this low pressure region doing in here? It's actually sucking the vehicle back up. So what you got when you put a set of rear wings right over your body is you're fighting yourself. You're straining real hard. This thing is pushing down like crazy, and it's trying. The total net result is not that much download. Now you might make it big enough and camber it enough so finally you get the download you want, but in the process of doing it, you've made a significant amount of drag. Now if you've made a lot of aerodynamic drag here, what in the heck is the advantages of putting this download on your wheels now? You're taking all that extra power to fight this aerodynamic drag. Okay, maybe it's helped you a little bit in the turn, but it sure as heck is hurting you on the straightaway. And you say, well, but I have so much horsepower, I need the torque for that wheel, so I need the tire to grab. Well, the reason you need the horsepower is because you got so much drag. So number one of the things you want to do is not put it over that. If at all possible, get it out here in the free stream region the best you can. Make your structure to do that. Hold it out here. Get it so that if this is the low pressure region in here, that it is not sucking the vehicle back up. Now, anytime it's within general proximity of the vehicle, it's going to have some effect on it. You almost can't get away with that. Maybe you can do something really clever by having it shaped this so that this low pressure region actually is pulling more air from underneath and helping your skirt. So by using that kind of aerodynamics, you're working better to help yourself. Another very common problem I see in these things sometimes is you'll see this highly cambered airfoil section sitting in here. And where do you want to hold this thing? You mount it right here with some big structure coming down onto it. This is the worst possible place you could do it. It's tremendously inefficient to do that way. Go back to this wing that we had over here a minute ago. This surface is very sensitive. It's a very smooth curved surface, and as the air is flowing here and going around this wing, it doesn't want to go over that wing. It's low pressure. It wants to separate. It wants to stall. And so what you're trying to do is make it as smooth as you can so it keeps attaching. Anytime you put a bar or some attachment in, immediately you're going to get flow separation. So as soon as you go in here, what you're happening? You're getting flow separation off of one of these things. You've got increased drag and reduction of downward force. So not only are you getting the drag of this intersection in here causing more drag, you're losing lift on it, and it's not just straight behind it. Let's take a look at what this would be if we look at it from a view looking underneath. Here is this rectangular wing, and assuming here is where your two struts sections are mounted. Not only will you have weight going back in here like this, but it will spread out in a 30-degree angle like this. So this whole region in here will increase the drag and reduce the lift. It's very easy by having poorly designed struts mounted on here to reduce the total lifting capability of that surface by 30 or maybe 40%. Very, very easy to do it. Again, if these are just round bars sticking out there, remember what I showed you in the beginning. That round bar here will have way more drag than this entire surface itself will do. You must make these streamlined. You must do anything you can to grab it in this region. If you have to come up here with some kind of bars, which is sort of a ridiculous way to do it, but anything to stay away from this part of the surface or the leading edge. Keep these things away from any kind of external attachments or perimeter tubing. The thing you can do is grab it from the sides. That's an excellent way. Anything you can do over here to the side of these surfaces and grab it so you get an end plate effect. Put some kind of additional surface in there to prevent the air from flowing around the edges of that airfoil section. It'll be good. And it's very easy to make this structure strong enough to go all the way across. You don't need supports in the middle to support that thing. Grab it from the two ends. Keep the smooth surface and the leading edge free from everything. Keep it away from the vehicle in here. And don't just guess at this shape in here. Don't go looking at somebody else's vehicle and say, wow, look at that kind of banana-shaped curvature he got on it and ground. It'll work, but not nearly as well as it'll work if you go back to the textbooks and look up the airfoil section and see what they can produce. It isn't very difficult to study this material and understand what it is, but there are very definitely airfoil sections that you can get that will be very, very efficient in producing your download with the minimum amount of drag. And of course, that's the main objective you'd like to have all the way along. There's a lot of work that can be done. There's a lot of work that will be done. I think the industry itself is constantly getting better and getting smarter in what they're doing. But anyone who's out there now who really wants to study the field and understand it and make some room, you've got virgin territory. You've got a lot of regions to work in. There's a lot of technology been developed by the NASA people and universities in aerodynamics that can now be applied to ground vehicles that will make the ground vehicle far more efficient, far safer, far better in handling, and much, much, much faster than anything we've seen. We just touched upon some of the key items in here right now. There are a lot more to be looked at. You can't make everything perfect. You can't get this vehicle down to the point where it'll do 200 miles an hour and 10 horsepower or something like that. But you can start aiming from where you are, from where you're at the present state of design of the vehicles, and continually improve and make them better. And also, this is an area too, when you have aerodynamics and you're going along at 180 or 200 miles an hour or whatever speed it might be, 100 miles an hour even, these things can be adjusted. These are maneuverable features. Airplanes have had controls on them for a long time. We can have a particular surface out there, and at one moment when we want to produce a certain force, we can produce the force. When we don't want the force, we don't. Airplane wings is a good example. We have flaps in the back. When we land and take off, we want this added lift. We don't care about the drag. We're not going fast enough. We put the flaps down, we come in for a landing. When we're cruising fast, we raise the flaps, make it smooth, reduce the amount of lift that that wing can give us, reduce the amount of drag, and off we go. These are other things that have to be considered. Of course, you have regulations and rules for different type of race cars, and you must stay within those rules and regulations. But even within those regulations, there is a lot of room that technology will allow you to go. And all it's going to do is make a better vehicle, a safer vehicle, and a higher performing one. Thank you.